Thank you. Yeah, thanks for being awake for the first session. Really nice to see so many people. Yeah, my name is Anton. I'm part of Juniper, but before I had some history as a service provider. So I worked for ISPs of various sizes. So you see this ladder. If you find yourself in the list of the ISPs, please come and we have a chat. We definitely have some things to discuss and to remind ourselves. Currently I'm doing the technical solutions architect role and working with service providers in EMEA region, so pretty large region. And today I will try to have a discussion with you on the topic of blackholing detection. This is a short agenda. We will go through the items quickly. But before we start, I would like to first set the goal. So there are many definitions what is blackholing. So not that we are misunderstanding each other. So if you are looking at the definitions, for example, from DECX, where you want to help a network to mitigate a denial of service attack, that's not it. So blackholing that I am going to talk about is actually something unintended, something that happens without you wanting it to happen, and usually very difficult to catch. So traffic is dropped, and let's start to troubleshoot. A few facts. Blackholing might have a long impact. It's very difficult to find. Every occasion of traffic being dropped unintended is too much. So you usually get a call from your CTO, CEO, you name it, depending on the size of your company. You usually need to escalate it highly, both internally as well as externally. So usually you would call a vendor, say what's happening? So why are packets getting dropped? We will start now with a few things. Scary things, why the things are so complex for service providers. So we'll be talking about usual landscape of a service provider. You would probably find some of your parts of your networks on this large diagram, but mainly we will focus on following parts. So we'll focus on aggregation, edge, core, and peering. And maybe some DC edge devices. So this is the goal of blackholing detection for today's talk. So the complexity of blackholing is that, usually how it happens today, you get a call from an angry customer, and then you try to understand what is happening. So you try to find out the source address, destination address, IS numbers, whatnot. And the complexity of finding a black hole is actually hidden behind how we operate our networks. Most networks would probably not run today the plain IPv4 or IPv6. So they would have some type of encapsulation. It can be MPLS, it can be SRv6, it can be GRE, whatnot, and it can be a mix of those. So there are many funny drafts and RFCs allowing you to put MPLS over UDP, over GRE, over something else. Then we have, of course, the control plane. We have really interesting topologies. So if you compare a service provider network to a data center, this would be like two worlds, two extremes. Service provider is something growing very naturally, where you need connectivity, where you have connectivity, where you have customers. It's like a snowflake without any distinct definition of where you have the links and nodes. Basically, the packets can get dropped on any device. And let's try to see first the complexity brought by overlays. So overlays that are used today usually were created to carry a VPN traffic. So we have layer 3 VPN, layer 2 VPN, different types, EVPNs and others. And they usually are encapsulated in MPLS packets. So you would mostly be having two MPLS labels in the core of a network. And imagine a P node, a core node, is dropping something. You would not have any awareness of the service on that P node, because the P node would not have the prefixes that are carried inside the packet. So this is one part of the complexity. Another part of the complexity is actually equal cost multipath. A bit unexpected because ECMP is usually something very beneficial. So you can offload your traffic from one link and distribute it across parallel links. So ECMP is a good thing. And ECMP is actually, to me, it is equal to link aggregation groups, for example, because the mechanism to split traffic across members of a LAG, of an aggregated Ethernet interface, is exactly the same, at least in Junos, as you would use for ECMP. And then on ingress nodes, like imagine on this PE1 node, you might be having equal cost RSVP or SRTE, SRv6, tunneling. So there are lots of ECMPs present in the network. And you can imagine that if you want to troubleshoot a packet flow from PE1 to PE2, and using it like with a trace route, you would probably not get the same path as if you would be sending customer packets. Even in one customer VPN, for example, if somebody is using, as in this example, DNS and HTTP, DNS might go over one path and HTTP over a completely different path. So this adds to the complexity of detecting where packets can get dropped. So before we proceed to some advices and best practices to remediation, let's see how network service providers, what mechanisms are they using today to detect blackholing. So you've heard yesterday as well good talks mentioning active monitoring. That's basically injecting synthetic flows where you have some test agents or some agents actually doing whatever, TWAMP, RPM, you name it. It can be even up to layer 7, so like voice over IP traffic injected over the customer's VRF so that you can qualify how good is the service offered by this service provider. So this is a good approach because it gives you really understanding how good the quality of the service is, but it's pretty expensive because, well, first you would need to have those test agents to inject the traffic, and second is that, well, if you want to be precise enough and to understand which portion of the network is having a fault, you would need to segment and to put so many test agents that it would be probably a bit difficult to manage. One way out of this is actually use the embedded mechanisms on the routers themselves, and we can do it already today with the synthetic traffic injection. Another way, a much more traditional one, is to do passive monitoring. So everybody of you is probably collecting different counters from your routing nodes. It can be SNMP, but I hope that you are using gRPC or other type of streaming telemetry, which is much more granular in time. So you can you are not limited by once in 5 minutes like with SNMP. Otherwise, your box start burning. But you can stream like once in 2 seconds if you wish, depending on the transport that you have chosen for your streaming telemetry. But you could, of course, use things like netconf or even screen scraping syslog. So to make it simple, if you compare passive monitoring and active monitoring is a good thing that shows you exactly which services are affected, just because, well, you put the traffic into the service itself. But usually it doesn't give you a hint where the problem is, because you don't have enough segmentation usually, because the two service points are located in different parts of the network. Well, passive monitoring is the opposite. It shows you exactly where the problem might be, because the counters are not all right from some device or some interface, queue, whatever. But it doesn't give you which services are affected. So these two need to be correlated in some way. And you've seen yesterday good examples that many companies are working in this direction. Before we proceed to remediation, let's first start with prevention. So good problem can be a good problem solution is when you prevent a problem and not remediate it. So we have two types of categories. The two categories how we prevent blackholing to happen. So some things can happen on box, but some things require some external controller or some external entity outside of the routing node itself. So let's take a few examples. You could be worried about, for example, shortest path first convergence on some nodes, like IGP SPF runs. You could be as well affected by slow programming of your forwarding plane. So nowadays, the routing tables are huge. So you have at least 1 million routes in IPv4, 250,000 routes in IPv6. You have multiple sources, multiple feeds. So the time to dissect this information in control plane has been decreasing over the last years because the CPUs are getting faster. You get more cores. The vendors are starting to create, their software which is not monolithic and running only on one core, but is distributed and threaded. But the forwarding plane is actually the ASIC. So we need to push all those routes down to your forwarding path. And this is actually what takes more time than the control plane convergence. So what happens if your control plane says, OK, I have selected my active routes in BGP, and I announce them to my peer, but it takes a few more seconds to push the routes downstream to the forwarding plane. Actually, that's exactly what happens. You have blackholing, because the forwarding plane will receive a packet, but will not know what to do with that packet. So nowadays, a few things to prevent this from happening would be, for example, put priorities on the routes. So you first inject, say, IGP routes into your forwarding, or you first inject the golden prefixes, if you wish, like, I don't know, Cloudflare, Akamai, Amazon's of your choice. Then in some implementations, we have as well acknowledgements between the fib and rib, which is a really cool thing that you don't only send the route down to the ASIC, but you get acknowledged how many routes have been programmed. And with this related feature is actually delayed route advertising. So if you don't get enough acknowledgements for the routes being programmed in the forwarding, you delay announcing those routes via BGP. So really cool thing. So if you didn't use it before, you might have a look at it. Then, of course, we have human errors. Everybody does mistakes. We have, people doing bad configurations, people doing bad design, which is even worse than doing the wrong config. Yeah, for this, we can only do the validation of the config in an automated way. You have heard as well lots of other people talking on this. I will not stop here for long. And yes, we have hardware and software bugs in software and in hardware, and we can detect those by some means, and that's one of the things that we will be talking in a minute. As well, on the topic of prevention, something that is very advisable is to analyze your control plane. Like you have your IGP and your BGP, which are main parts of your control plane, probably. And in IGP, there are many very dangerous scenarios where you have duplicate sysids, host names, prefix seeds. If you use segment routing, then you need to monitor the SPF runtime. So something that not many people pay attention to. But if your calculation of the shortest path in your ISIS or OSPF is getting longer over time, that's a clear indication that your network might collapse at some point in the future. So better prevent it. So take those counters, analyze them, apply machine learning on this. Because this is a perfect example of machine learning where you could detect a sudden increase of the SPF runtimes. Similar to BGP, I will not spend much time on BGP, but very similar examples can be brought in here. So trying to help the industry itself and our customers and our teams, we have introduced a resiliency interface, and part of this resiliency interface is related to sampling the packet and the metadata of the packet that is going to be dropped. So really interesting use case. Like imagine that you have let's take a sample scenario. Okay, so a sample scenario, we have a P node, and it's going to, or it should be forwarding some packet. And this packet is an Ethernet encapsulated packet with 2 MPLS labels because it's part of some VPN. And then we have all layer 3, layer 4 information. At the end, we have some HTTPS data, which is part of this packet. And then something is wrong with this P node. So it doesn't know, it doesn't understand the top label, for example. Or something wrong on the Ethernet level. So I don't know, wrong VLAN, wrong destination MAC address. There are tons of issues that can bring this packet to be dropped. And actually, the worst thing is that usually the ASIC does care about dropping this packet, and you don't get much feedback in the CLI. This is what usually happens in modern operating systems. So we can make this work better. So we can pre-program the node that in case it wants or it needs to drop the packet, that it has already a pre-configured collector, and it will send part of this packet, so part of the payload, say up to 250 or something bytes, all of the headers of that packet, and the metadata to the collector. So what that brings to you as an operator is actually you get an IPFix packet, which is easy to decode, and you see which node has been dropping, on which interface the packet is incoming. You see the direction of the flow, ingress or egress. You see the exception code, so why the packet has been dropped. For example, I have no route to the destination, or I don't know, so the MAC address is invalid, and so on and so forth, or maybe firewall filter. And then you have the full headers of the packet and part of the body of the packet, so that in one IPFix message, you can immediately understand the root cause, not the root cause maybe, but at least the exact thing what has been happening. So you have all of the details required to react immediately and without involving very difficult troubleshooting on the PFE or on the ASIC level. Two use cases we see as a primary use cases for such approach. One is that we just discussed the blackholing event. Say we have a packet incoming, decision is drop yes or no, and if we drop, we could have an action to export. But if we forward, we have as well a possibility to export this packet to the collector. This is a good second use case where you want to monitor one certain flow out of tens of millions of flows going through a router, and you can define the flow by usually using a 5-tuple, source, destination, port, address, TCP, and so on. But you could as well use on some platforms what we call flexible offset filter, so that you define that I want to start the offset from layer 4, so the router will know it would find TCP or UDP, and then you say you take 2 bytes from that offset, and from those 2 bytes the last 3 bits, and compare them with some number, and then it will be a match. So you could actually define, for example, if you look for DNS request, right, with a certain name in it, a resolution for an A, then you could actually match the exact string inside the packet and then export it to a collector. So as we say, pickup already didn't happen, so I want to see it on the wire. On the wire, we would have actually this IPFix packet. You would have it as a, well, you could decode it with TCP-DUM or T-SHARK, the outer part of the packet. But then, as I said, there is as well a payload of the packet itself with all of the headers, not only metadata, but the payload in blue in this case. Well, you could use a string like this on the top. Really, you might have heard of some of those utilities. Or, of course, you could use some dissectors that are available and don't require this amount of pipes in one line. So you could go with a GoFlow2, or you could go with a PM-ACT. So both of them understand IPFix. Both of them can decode the packets. Or you could use, again, the string that I've used in this example. And then you see, all of the headers. It was 2 times MPLS. It was IPv4 with some UDP inside, port this and that, and so on. Well, if you trust, you could use as well LLM, right? But then you're on your own. So if LLM has some hallucination, it can give you some random results. Well, you need to be careful with LLMs nowadays. But yeah, it's easy to drop a packet into ChatGPT and say, decode this for me. The result is unpredictable, however. So, right, the exception list, just a quick overview. You could use this type of blackholing detection on your peering nodes. For example, like if your firewall drops the packets for some reason, or maybe if the source MAC address is not in your allowed list, you could use it in the core with your SRv6, MPLS, or what type of encapsulation you use, and so on. The packet itself, as said, it is IPFix. So you have 3 things streamed by the routers themselves. You have the data template, options template, and data record itself. In the data record, you would have the packet clip and all of the metadata that we discussed. And we are working with IETF to get it standardized. So if you are active at IETF, please support. Correlation is a big thing. So that's really difficult to understand what is happening. And with correlating things, we need to take care that keep in mind that somebody is doing a change in the prefix list on one side of the network, but dropping is happening completely on the opposite side. So that's a tough thing to solve. This is something where there are different approaches you could use. For example, for a service dedicated LSP, but then you would not have ambiguity of ECMP, but then you have back the problems of elephant flows or large amount of LSPs. Then you might be covering your whole network with the point-to-point LSPs, but then again, the amount of LSPs is high, and then again, you need to correlate it in some way. We have some other things that we have seen in the wild that people do inject a specific cookie in the packets. So some inject packets with some specific bits present in that packets, and they catch those packets with filters on the transit nodes. And if you did not see this packet, you will be probably looking at the right device that is dropping. So now, in the automation side of things, we have as well, we are at the beginning of this, right? So you collect this, of course, all of this telemetry. Without telemetry, you don't have a possibility to do any automation. Then you have some correlation service that will be usually some magic source from your vendor, or it could include some of the AI, and we have high hopes. So this is something where LLMs are really good at correlating stuff because they need to dissect lots of inputs from many sides and understand what is happening. So we really have high hopes on this. And at the end, you will have the service that tells you that things are going bad, things are happening, and maybe providing you a root cause. It was a link event, or it was maybe some BGP update that caused the problem. We have as well our own software doing all of that. I will not do any marketing on this, but at the end of the day, you would be able to see in the UI that things are happening, this device is dropping packets, and maybe the problem is because of somebody is doing some commit on some device on the network. So the correlation is there, and causality is something as well that we're working on. So I have rushed through the couple of slides at the end just because I wanted to give some time for the questions. I didn't want to actually to leave the stage without letting you ask anything.
Thank you, Anton, for this interesting talk, and we do have a bit of time for some questions. So are there any questions? Please raise your hand. There is one question. Please state your name and affiliation. And
Elmar RT-Brick question, sampling all these dropped packets, is that chip native or do you need a service card or anything to do that?
Great question. That's actually exactly why we have chosen IPFix. IPFix is UDP, connectionless, doesn't require TCP. Well, you don't need to have acknowledgements. And this is native in ASIC, so ASIC can export the packets line rate. Sure, you need to make sure that you have enough bandwidth.
Any other questions? I do not see any raised hands in the room. Do we have anything on Venuless? No. Okay. So there are no questions online. Then thank you again for the interesting talk. That's a wrap for this one. We'll be right back with the next talk. And don't forget to rate the talks.
Thanks.